In this section, we will discuss standard turning inserts. By standard, I mean tools that can be coded based on ANSI or ISO standards. So first, let's discuss how turning inserts are represented by a code based on these standards. The turning insert shown here can be represented by a code like CNMG 432 or CNMG 120408. The first code represents this insert in inch or imperial format, while the second code represents the same insert in millimeter format. The first character of this code, which is a capital C, represents the shape of the insert. The shape is a rhombus with an angle of 80 degrees. According to the standard, the first character of the code for an insert with this shape is a capital C. If the insert has a rhombus shape with an angle of 55 degrees, its shape is represented by a capital D. And if the insert is round, it is represented by a capital R. This coding continues based on the insert shape table that I've shown here. You can also see a picture of a CNMG insert and a VNMG one. The CNMG insert has a rhombus shape with an angle of 80 degrees, and the VNMG has a rhombus shape with an angle of 35 degrees. At this point, before moving forward, I want to talk about different types of operations like roughing, finishing, continuous cutting, and interrupted cutting. To convert raw material into a final product, many operations are involved, such as roughing and finishing operations. A roughing operation, generally speaking, is used to remove a large amount of material quickly and to produce a part geometry close to the desired shape. The cutting forces in roughing operations are usually higher compared to finishing ones. On the other hand, a finishing operation usually follows roughing and is used to achieve the final geometry and surface finish. In interrupted cuts, the cutting tool engages and disengages with the material, like when trying to turn a square. In continuous cuts, the cutting tool is engaged with the material all the time, and cutting forces remain more consistent. Now, back to insert coding. Generally speaking, an insert with an R or round shape has the strongest geometry, making it very suitable for roughing operations or interrupted cuts. After the R shape, the S or square insert comes next, followed by C, D, and finally V. You might ask why we don't always use the R or round shape since it's the strongest. The reason is that sometimes we need access to a position in the part where the R or S shape cannot reach. This is why we use V or D shapes. I have summarized this in the picture. The second character of the code represents the insert clearance angle. The clearance angle is defined as the angle between the side edge of an insert and a vertical line starting from the tip of the insert downward. In these pictures, you can see different code characters for different clearance angles. P represents 11 degrees, C 7 degrees, B 5 degrees, and N for 0 degrees. If the clearance angle is 0, the insert is called a negative insert, and if it is not 0, like 11, 7, or 5 degrees, it is called a positive insert. In the left picture, you can see a CNMG insert. As you can see, the angle between the side edge and vertical line is 0. Therefore, based on the standard, the second character of the insert is N. On the right picture, there is a DCMT insert, and as you can see, the angle between the side edge and vertical line is not 0, it is around 7 degrees. Therefore, the second character of this insert code is C. Now, you might ask what the importance of the clearance angle is and what role it plays in machining. Generally speaking, inserts with larger clearance angles are considered weaker compared to inserts with smaller or no clearance angles. So in roughing operations, we use inserts with no clearance angle like CNMG or RNMG. On the other hand, higher clearance angles result in lower cutting forces. Therefore, in finishing operations or situations where we don't want to generate high cutting forces, we use inserts with larger clearance angles. The third character represents tolerances on different dimensions of an insert. The tolerance depends on the insert shape and its size and can be represented by C, H, E, G, M, and U. Generally, H represents the tightest tolerance, but M is the most common one, followed by G. When choosing your insert, you should not worry about this character too much. If you choose an insert with the third character as M, it should work fine. Other tolerance classes like H are important for special machining operations. In the standard, there are tables to find the tolerances that inserts are manufactured accordingly. The fourth character of the insert code represents insert features. This refers to whether the insert has a hole in the middle, whether the hole has a chamfer, if the insert has a chip breaker, and whether the chip breakers are on both sides of the insert. A chip breaker is a geometry at the top of the insert that helps break machining chips. Generally, an insert without a chip breaker is considered stronger. So ceramic inserts, because of their brittle nature, usually have a feature code of N or A, meaning no chip breaker. The feature code of M usually represents a stronger insert compared to the G code. As you can see from the pictures, the feature code M represents an insert with a chip breaker on only one side, while the feature code G represents an insert with a chip breaker on both sides. Having a chip breaker on both sides makes the insert weaker, but chip breakers are helpful for breaking chips when machining materials with long chips such as titanium, aluminum, or stainless steel. Therefore, a CNMM insert is considered stronger than a CNMG insert because it has a chip breaker on only one side, making it more suitable for roughing or interrupted cuts. The fifth component of the insert code represents the size of the insert. D represents the theoretical diameter of the insert's inscribed circle. The table shown here displays the relationship between inch and millimeter coding and how they are determined based on the insert's inscribed circle diameter. For example, if the insert has a rhombus shape with an 80-degree angle, the shape code will be C. If the insert's inscribed diameter is ½ inch, the size code in inch coding will be 4, and in millimeter coding it will be 12, as shown in the table. Generally, a larger insert is considered stronger and capable of making bigger cuts, but it is also more expensive because it takes more material to manufacture. The sixth component of the insert code represents the insert thickness. This table shows the insert thickness in millimeters and its corresponding symbol. For example, the insert code CNMG 20408 represents an insert in millimeters with a thickness of 0.4, meaning the insert has a nominal thickness of 4.76 millimeters. Similarly, for an inch-based insert, such as CNMG 432, the thickness symbol 3 corresponds to a nominal thickness of 3/16 of an inch. The seventh component of the insert code represents the corner radius. In the picture of the VBMT insert, you can see the corner radius, which is the fillet between two edges of the insert. Like insert thickness, there are tables for millimeter and inch coding for corner radius. When choosing an insert, special attention should be paid to the corner radius, as it is an important factor. For roughing operations, a larger corner radius, such as 12 or 16 in millimeter coding or 3 or 4 in inch coding, is recommended. For finishing, 0.4 or 1 in millimeter and inch coding, respectively, are suitable. These 7 components are common across all standard turning inserts. However, tool manufacturers also use specific codes for chip breaking geometry and insert grade, which are specific to each manufacturer. Chip breaking geometry, or insert geometry, is the design at the top of the insert used to control chip length. Chip breaking geometries are often specific to certain material groups, such as steel, cast iron, or stainless steel. Now, I want to discuss material groups and what they mean. In metal cutting, materials are divided into 6 groups: P for steel, shown in blue, K for cast iron, red, M for stainless steel, yellow, N for aluminum, green, S for heat-resistant alloys such as Inconel and titanium, and H for hardened steels. Insert geometry greatly affects the cutting edge strength and cutting forces, so some insert geometries are suitable for roughing and interrupted machining, while others are ideal for finishing operations. For example, Sandvik uses PF, PM, or PR codes for different types of geometries. The logic behind Sandvik's insert chip breaker code is simple. P indicates the chip breaker is suitable for P group materials, meaning steels, while F stands for finishing, M for medium, and R for roughing. So, PF is a chip breaker suitable for finishing operations on steel, PM is suitable for medium operations, and PR is suitable for roughing and interrupted operations on steel. Similarly, you can have KF, KM, KR, MF, MM, MR, and so on. Inserts are also distinguished by their material and coatings. Each company has its own codes for these. For example, Sandvik has codes like 42115, 4225, and 4235. Sandvik's coding system is logical and easy to remember. For example, Sandvik's turning grades for steel, P group, start with 4, for cast iron, K group with 3, and for stainless steel, M group with 2. Let's talk about the last 2 digits of Sandvik's insert grades. Based on ISO standards, each material group, such as P or K, is ranked from 01 to 50, with 01 representing wear resistance and 50 representing toughness. The last 2 digits of a Sandvik insert grade represent this ISO ranking. So 2015 has an ISO ranking of 15, 2025 is 25, and 2035 is 35. Therefore, 2015 is more wear resistant than 2025 and 2035, while 2035 is tougher and more suitable for interrupted and roughing operations compared to 2015 and 2025. As an example of a complete turning insert code, consider CNMG 10408PF4225. This is a millimeter insert, and in inches, the same insert would be CNMG 432PF4225. C represents the insert shape, N the clearance angle, M the tolerance class, G the insert feature, 12 and 4 the size in millimeters and inches, 0, 4, and 3 the thickness in millimeters and inches, and 0, 8, and 2 the corner radius. PF represents the insert geometry, and 4225 the insert grade. Remember, when ordering an insert, you should always include the insert geometry and grade. Okay, this section was a bit longer, but I think it was very technical and useful. In the next session, I will talk about standard turning holders.